For the very last thing I'll show you in these videos, we're going to do a neat trick that we can do with Stokes Theorem, right? So Stokes Theorem allows us, in essence, to take into a surface integral, a flux integral, of the curl of f dot ds and change it to an integral over c of f dot dr, where c has the orientation induced by s. Right? Well, think about this for a second. Suppose S1 and S2 both have boundary C. Right? Suppose they both have the same boundary, okay, and both induce the same orientation. On C. Well, then this guy up here, well, let's call this one S1, but that's, from the other side, that's the same thing as saying integrating. If we start, say, with S2 and use Stokes Theorem to go to the line integral, we get the exact same one. So what has happened here is we've switched the surface S1 for the surface S2, right? That's a neat little trick that we can do with Stokes Theorem, right? So I tend to call this surface swapping, but typically the way this works out is you have some horrible surface S1 with boundary C, and maybe you can find a nice surface S2 with boundary C. Then you can use Stokes Theorem to switch from the horrible surface to the boundary and then back to the nice surface. And you usually do this when, you know, maybe curl F is already kind of nice, or maybe trying to do this line integral over the boundary isn't so pleasant. So what would be an example of something like that? Well, here's one. Let's say S1, oops, not upper one, this lower one is the boundary of the box, which is given as sort of the unit cube here, if you like, with no bottom. Right? So you have that six-faced cube and you tear off the bottom square. Right? So S1 then is a surface that looks something like this. Draw some more lines here. Right? So this would be S1, this cube, right? Where the red here, the pink here, is meant to denote the boundary, which let's just call the boundary C instead of boundary S1. Right? All right, and let's say this has the outward orientation. So the orientation that looks like this. Right, so it's kind of going outward from that box. All right, well, what orientation does that induce on the boundary? I'll let you verify that it's the counterclockwise one. So here, you know, z is up, x is out, and y is this way. All right? So Well, if you think about it, if we do this flux integral across the surface S1, we're going to have to do 5 flux integrals, 1 for each face of that box. That's, that's kind of rough, right? But can you think of a nice surface that also has this boundary C, right, with that same orientation? Can you think of a nicer one? So here's C again. So hopefully you're thinking about just filling in that bottom piece that was missing, right? 1 square is a lot better than 5 squares, right? So what should the orientation on that look like? Let's use blue because I think the green might clash a bit. Well, we should again want the upward orientation on the bottom of the box, right? So by using Stokes theorem, we switch from the integral over the 5 boxes to the integral over the boundary, right? So here, this is 5 flux integrals, right? But if you just use Stokes theorem once and you go to C, this is 4 line integrals, right? Because you're integrating over a square, like your curve is a square, so you have 4 components to integrate. But, let me just call this C instead of underlining it. But if we go down here to S2, this is 1 flux integral. All right? So that's the benefit of Stokes theorem, or another benefit of Stokes theorem, I should say, right? Is it lets you swap this messy, terrible surface for one that's nice. All right? So I'll leave it at this. Hopefully this has made sense to you. Hopefully these videos have helped you in learning Calc 3.